Okay, we can start with the talk. So let me just a second. Yes. So, hello everyone. Myself Gaurav Kumawat, coordinator of ISER Bhopal Astronomy Club. With the beginning of the new semester, I welcome you all to the first club talk by IBAC. Today we have with us Mr. Atharva Bagul from BSMS 2018, Department of Physics. He will be giving a talk titled Brown Dwarfs, Failed Stars or Overachieving Planets. We will be having the Q&A session at the end of the talk. You can keep posting your questions in the chat box. We will take note of the questions, and if there is any urgent question or doubt in between the talk, then you can use the raise hand option for asking the question. And now I welcome Bhaiya to take off from here.
Okay, thank you. Thanks, Gaurav, introducing me. I'll skip directly to the talk ahead. If anybody has any questions, feel free to just raise their hand and start talking. Um, Later on, we can have a question answer session, obviously, but in between, I prefer in between also. Okay, so let's go. So we want to focus today on brown dwarfs, which may be called as failed stars, which may be called as overachieving planets. These were priori called black dwarfs, very long back, but black dwarfs was then taken up by the name was then taken up by the class of like the state of a star after the white dwarf stage. So that's why now we have come to the concept on brown dwarfs. So these are somewhere between planets and stars. We want to look at the similarities of brown dwarfs as objects with stars and planets too. So I would start with something basic, which is spectral types of stars. This is a mnemonic, but okay, only bad astronomers feel good knowing mnemonics. So it gives O, B, A, F, G, K, M. These are the spectral types we know. Just to tell you the basics of it, that O spectral type comes with surface brightness temperature greater than 25,000 Kelvin. Uh, then B comes with between 25,000 and 10,000 Kelvin. A in above 7,500 Kelvin. F above 6,000. G above 5,000. K above 3,500. And M above 2,300 something. So these are the surface brightness temperatures that surface temperatures basically that like we classify them. We also see pretty spectral features for these particular stars. So spectral type O, we mostly see ionized helium, which more comes in a blue color, and spectral type B, we see helium and some hydrogen. Then the color is from white to blue. A is in the A type we see strong hydrogen and then some ionized metals. So about metals, astronomers call everything beyond helium, apart from hydrogen and helium, as metals, because majority of lifetime of the stars and other objects, it goes in hydrogen and helium, fusing hydrogen and helium only. So A type has some ionized metals also, and it is in white color. F type has hydrogen, then ionized metals, mainly like calcium and iron. So it goes, as you can see, like yellowish to white, yellowish white color. G is yellow color with metals and ionized metals in it, mostly ionized calcium, majority of it. And K is mostly all metals, orange. And M is strong titanium oxides and some other calcium compounds, so it is red in color. About so three best examples that we can look at in star. Okay, hello, Gaurav. There is some technical problem over there.
Yeah, I'm looking into this.
Okay, so Shall I continue or shall I pause?
Yeah, you can continue with the talk. The talk is recorded. It will be uploaded on the YouTube channel, so you guys don't need to worry about it. You can watch the lecture after the talk as well.
Okay, so I want to give three basic um, co- co- examples for stars which in their later phase of life. So giant stars which are basically low mass stars nearing the end of their life. So they come in the spectral type mainly G, K, and M, with radius about 10 to 50 times the radius of our sun, and mass about 1.5, 1 to 5 mass of the times the mass of our sun. And there are then white dwarfs, which are dying remnants of imploded stars. Their spectral type is D. It is somewhat kind of a different spectral type because it has surface temperature very high, so about less than or comparable to 80,000 Kelvin, and it has it has a very small size with like 0.01 times the radius of our sun. And as you know from the Chandrasekhar limit, it is less than 1.5 stellar masses. And there is a third example about supergiant stars. So these are high mass stars nearing the end of their lives. Um, they encompass the spectral type of the entire uh, spectrum. So O, B, A, F, G, K, M. And they are about very huge. So 330 to 500 stellar radii and 10 to 70 stellar masses about. But these have very low abundance. So it's like 10 raised to minus 4 of a percent, maybe. Yes, that's the abundance we're talking about. So this is small video. We just want to zoom in or zoom out from ourselves to our neighborhood to look at what we have around us. We start from the sun, the solar system. Then we come across the Oort cloud. It's a, After the solar system, we come across the Oort cloud. Then the Alpha Centauri, and then we have our rest of the stars. So currently, we are only trying to focus on the first 10 parsecs. So maybe I'll pause after the 10 parsec thing. You can obviously see the rest of the video. It might be available on YouTube. So this is our 10 parsec. Um, there are so many objects, so many stars, and mainly we have this in our 10 parsec area. So to give a feel of it, 10 parsec is about 33 light years, and we can see similar range stars in like 19 to 20 stars which have are similar to the sun. 10 to 11 are very much massive than the sun, and 327 less massive than the sun. So there is a huge population which is less massive than the sun. And and we have 50 brown dwarfs in this 33 light years distance, like a radius from uh, our sun. So what is it between stars and planets? So basically, if we start from our rocky planet thing, if we go to ice giants and then gas giants like Jupiter, we come we go above that in some mass range. There is this huge gap between gas giants and low mass stars, which we kind of try to fill in with some objects. We name them as brown dwarfs. They range from 13 Jupiter masses to about 75 Jupiter masses. This is purely mass based, so I have not come yet to the properties of brown dwarfs. This is just how we classify them based on their masses. Um, so it is important for us to um, get to know how we can see our sky in general, because we can see it in many different wavelength and frequency ranges in bands, but we can see different aspects of the same object in different frequency bands. So over here we are looking at the visible and the infrared. This is the same object, Orion Nebula, but we can see complete different things in the visible and infrared. In the visible, we can see the the trapezium stars, the cluster just uh, which is just there, but in infrared we can actually see the dust in the nebula. So this is important because brown dwarfs also have some kind of brightness temperature range, and therefore they will emit in some kind of frequency band and in not all of them. Um, After that, we want to see how stars are identified, maybe the proper motion. So like there is a stellar background, and there is this background, and there is one object moving comparatively faster than the background. So either we can call that our aeroplane, even if we can call that a star, a brown dwarf, or basically relative motion we look at. So this is a small video which gives us one star. I don't know from where I picked it up, but I'm sure I can give you the reference also. So this proper in 1980 or 1978, uh, Kevin Lumen discovered this system of brown dwarfs, which is closest to the sun, like the closest brown dwarf system we have. And surprisingly, these are Lumen 16A and Lumen 16B. So this is a binary system of brown dwarfs, which is also characteristic of stars, if I'm correct, and not of a planet. So like we find binary system in stars. So we have kind of a overlap between planets and stars, which we like to um, say that these are some kind of objects over there. So the closest brown dwarf are there, Lumen 16A B, the system, which, yeah, okay, this was taken in 1978. This was confirmed by various telescopes. So like over a set of many 10 to 20 years, observations were taken in many different telescopes, and we can like they compiled everything to confirm that this is not a binary star system but binary brown dwarf system. And there is this wise, not a good name, but okay, this is the second closest to them. So if we look at our nearest neighbors, we have the sun, Alpha Centauri, Bernard star, Lumen 16, and Y0855. So basically, the fourth and fifth nearest neighbors are not stars, but are what we call them as brown dwarfs, somewhere between. So this is a general what a stellar structure looks like. So radiative core and convective core. I think you all have learned this in some or the other sense. What goes on in the sun at the center. This is just a basic rough process outline, not any detailed calculations of stellar nucleosynthesis, though. Uh, we are interested in this as we want to look at something less than the red, the rightmost circle that we have, something beyond that. So, where there is not much energy, there is not much mass in the brown dwarf that it can fuse stuff and it can radiate in that sense. So, these are, we know the Earth and our planet Earth-like planets and other bit planets which are like glued together, I would say, by gravity, but there should be one force which acts opposite also, which is the solid and liquid pressure that we have. And we know to counteract gravity, we have nuclear fusion in the stars. But we can't have nuclear fusion in the brown dwarfs as we don't have that much mass. Although there are some very high mass brown dwarfs which fuse deuterium to some level and they glow slightly, not that much, but they glow slightly. But that is again the borderline between brown dwarfs and stars. This is a very famous picture up here by NASA when they were trying to explain what exactly the Pauli exclusion principle is to a kid. A kid is undergraduate student, so basically who doesn't know the physics of it, the maths of it, I would say. But okay, so when you have an empty car space, obviously you can go and park anywhere, and there would be normal, uh, normal speeds. But when you have only one space for many cars to park, you would have rush, and there would be pressure, which would be called. So same thing is there in the Pauli exclusion principle. One one state can only acquire one fermion. One quantum state can only acquire one fermion, and there is no place for the second fermion to be there. But when the states are full and when there are many fermions racing for the one quantum state, we have high pressure. The pressure develops, and this is something that actually keeps the brown dwarf together. This basically counteracts the gravity, if we would say. And this is the case with large gas giants also, like our Jupiter or hot Jupiters and bigger than Jupiter planets. So we can see that there is a similarity between stars and brown dwarfs, as in they they come in binary systems. They are not like they are unlike planets, as in if they can host something. They come isolated in picture. They don't have moons revolving around. They have moons revolving around them, not much. You can find a few, and it comes with a bit some of the similarities with planets, as they keep up against their gravity by equal by the forces which gas giants and more like massive Jupiter like planets do by the electron degeneracy pressure. So we tend to put them somewhere in the transition zone, not transition as in evolution transition zone of a planet and star, but like in just the flow. So there is this very typical property of a planet which also resembles to the brown dwarf is giant planets like Jupiter's and all, they cool with time. So in our solar system also, Jupiter started out very hot near the star, near our sun, and it cooled down with years and went at the back of the solar system, so like away from the sun. This happens with brown dwarfs too. They also cool with time, about 3,000 Kelvin to 1,000 Kelvin to further 250 Kelvin. Most of so these lesser temperatures, lesser than maybe 2,000 Kelvin temperatures, we need some classification renditions to our spectral type classification of our stars. So we add these three classes, Y, T, and L. It's like 1300 Kelvin to 2300 Kelvin, 450 to 1300, and less than 450. So less than 450 Kelvin is most of the gas giants that we can also see. Um, Jupiter has Jupiter has a temperature of 128 Kelvin surface temperature, it puts it in the white dwarf zone, but it is a planet. So we need to understand that also. We so most of the brown dwarfs have temperatures, even which surface temperatures which can be like human body temperatures, or or some kind of temperatures that our household oven can also reach. It is quite fascinating that such low temperatures also exist, but they are not planets. So yes. Another thing we can take from stars is their atmosphere. So as we discussed in the first slide of the stellar spectral features in the stellar classification, we had many various compounds and many various elements showing up in the spectral features of the stars. So we can see these particular as written over here: hydrogen, helium, titanium oxide, calciums, different calcium compounds, and vanadium oxides, and all heavy metal oxides in smaller stars. In those like K and M classification, if I may. Yes, and then we have the brown dwarf weather. So it is kind of similar to the smaller star weather. It goes on increasing with the heavy metal oxide, and we have this in particular for the T dwarf. We start with we have these L dwarf and the ML transition. So as you can see, the calcium titanium oxides in the M/L transition zone is kind of up in the upper half of the atmosphere, and as in when we go below the classification thing, as we go from L to T to then Y, we can see the calcium titanium oxide settling down and more oxides and more sulfides getting added on top of it due to the temperature changes. So this is the basic brown dwarf weather, so, which is an extension of the stellar weather. Low mass stars M, then L, then T, and then Y. So I have not shown Y over here because I don't know exactly what Y has, but okay. So this is so we kind of place these with similar properties as stars also, because we can just extrapolate the stellar classification directly into a brown dwarf classification, the spectral classification, that is. Now, how do we study these these particular brown dwarfs or the high mass, sorry, gas giant planets and all like Jupiter's? So we have these clouds which people saw. Um, and so over here you can see there are these clouds which people saw. These are not perfect images, but these are artist renditions of the what we have seen with our surveys. So we can see some kind of clouds on those, just like Jupiter, and we can trace those clouds in order to um, study the variability. So in general, such pictures are taken, such flux versus the rotation degree angle is measured, and then we can completely map the cloud structure and the planetary type of structure of that brown dwarf. And this is taken from the Artiga 2018 paper. So and then we have established till now that brown dwarfs are truly there in between the Mars to planet transition zone, and they follow properties of both. Uh, so I have a very vague idea about how can we draw up analogies. This is a very interesting paper I found, which actually studies 38, I guess, um, sumo wrestlers and 39 normal males in the university, and they find some graph of fat-free mass index versus fat mass index. It doesn't matter what these quantities are with our things, but so we can see clearly that there is one group of red dots on the upper side and one group of blue dots on the lower side. If we kind of plot such similar things with such similar analogical quantities, we can also see that we can get such a distribution of the stars and the planets with certain properties, and we can find our brown dwarf somewhere in the middle with the crosses, where the crosses are. So this is just relating something non-physics to physics. I like doing that as it gives a bit realistic feel of what we are doing. So our aim is in particular to fit brown dwarfs in between, and this is the ongoing research. So basically, they have not yet found the perfect kind of fit for brown dwarfs, as they are now finding brown dwarfs which have some kind of nuclear fusion going on in them, as I mentioned about deuterium, and they also are finding some brown dwarfs which are very closer in mass structure to the closer in mass in the property structure to the Jupiter. So there is a still varied big question that where do these guys fit in? So I guess that's it from my side for now. I guess I'll answer the questions.
Yes, thank you. So now we can move on to the questions. First of all, you guys can ask your questions. You can raise your hand and ask questions, and then we will move on to chat questions in the chat box. Hima, can you send me the questions that were asked in the chat box?
Yep, just a second.
Questions regarding IBAC and its procedures and all, that will be answered in the next session. So that will be the orientation session on 25th.
Isn't it open for all? Why do you need to join the club? You just attend the meet,
Yeah.
take part in the discussion.
I guess he's asking about core member.
He's
It's
asking
far
about the
away.
core committee and all.
Okay. So I guess we can
Come on,
move
guys, you can
towards
ask.
questions in the chat
Come on,
box,
guys,
I
you can ask your questions as well. No need to hesitate here. Okay, so there are questions in the chat box. First is, if there would be no fusion, that means not much bright, then how are they discovered then? Here,
Yeah, there are different surveys which are okay. There is one hand going up. Okay, he left the meeting. Okay, nice. So there are a couple of surveys which were employed, like Spitzer by NASA and couple of others. So they were mainly looking at the background thing, and they were mapping just like some star. And at first they didn't figure out that it was something of us. It was something like a it was something like a star, but they did notice that it was exoplanetary, to be fair, but not exactly exoplanetary because it was not revolving around certain thing. So it was discovered by polarimetry. There is a, if you want to uh, like talk read about it, you can read about it. the method was polarimetry. It was used. Polarimetry is basically polarimeters are basically um, are polarized glasses for astronomers. You can visualize it as that. Okay, there is one hand going up. Just unmute and ask.
Yes, Barnali, you can ask.
Are white dwarfs brighter than these brown dwarfs?
Yes, yes, absolutely. White dwarfs have surface temperatures about 80,000 Kelvin, and brown dwarfs don't even have about 1000 to 1500 Kelvin. Like the max we know is 23,000, 2300 Kelvin of a brown dwarf,
Okay.
which is very near to the lower mass star M classification. So these are certainly white dwarfs are brighter than that. But due to the apparent size, white dwarfs are very far and such brown dwarfs are very near. So that angular size also matters while we are detecting something.
Okay, sir.
Yes, Devang, you can go
Devang?
on.
Yeah, so my question was about the new classification of brown dwarfs called sub-brown dwarf stars. Can you, can you explain
I
more
have I
about
have
it?
I have no detailed idea about that classification. That is somewhat of a research topic. So
Okay, because they have said like literally that sub lower mass limit for sub-brown stars should be around Jupiter's mass,
yes,
but
it is
that is
certainly about 10 or 13 times of the Jupiter mass. If I remember correctly.
yeah. But my confusion was if it is just around Jupiter's mass, exact. So like we should see other planets like Jupiter itself also be under the category of sub-brown dwarf stars.
Yeah,
But
but
it
the main point of planets is they orbit around a star, right? So these
yeah
brown
yeah
dwarfs
yeah.
are independent entities. They don't orbit around some certain star they orbit around some systems, but they don't orbit around a certain star with that particular angular velocity and that frequency of oscillation.
Okay, I get it. Thank you.
Ankit, Ankit Kumar Haripal. We can have Samir Verma, anybody.
I want to ask that, like, they are named brown dwarf. Is brown suggestive of their color, or they use it like, मतलब ऐसे ही use
I
कर
don't
लिया
think
brown,
so. It is
but
suggestive of anything, but most of them have heavy metals and heavy metal oxide in it. So the atmosphere makes their color kind of dark. That's why maybe it is called those.
and like lumen systems you mentioned, do most of them occur in a binary star
No,
system
they,
like?
they occur singly also and in a binary system also. So they
Okay.
occur just like Jupiter high gas giant planets, and they occur like low mass stars in a doubly binary system also. So there is no particular distinction about how many. I bet there would be statistics of how many occur in what sense, and we can draw something from that, but I don't know about that.
And my last question is that when we were talking about the cloud formations, like you talk, you said something about flux, and I was not able to understand what was that flux, which kind of flux, what kind of flux.
So it is basic flux pretty much. So uh, what is flux? So like amount of photons amount of photons incident on our detector plate, right? In certain amount of time.
Okay, okay,
Yeah,
like
yeah,
no, I was like, matlab, what was that flux?
yeah.
Electromagnetic flux, magnetic flux, electric flux.
Its general flux is that idea. Now it depends on the researcher what he is using. You can refer to that paper maybe if you want details of it. I'll showcase that slide again. It's Artiga 2018.
Okay, thank you.
Utkarsh.
Yes, sir. Sir, my doubt is, sir, all these we are talking about brown dwarfs. They have something moon or their own planetary system. Means, sir, are they potent enough to form their own planetary system?
We don't know any of them which have their own planetary system, and they are not potent enough because they don't have that much gravitational pull towards anything as our sun has. You can also notice that not many of the lower mass stars also host any are capable of hosting any systems like such.
So, sir, they couldn't have anything like moon also.
They can have a moon, they can have one satellite object rotating around them, but mostly it is not the case because these themselves are very independent entities and they don't orbit around any particular given object. They tend to orbit around the galactic center and thus some objects, some systems, but they don't orbit around any particular star. So they can't orbit around something. They are pretty independent and they mostly don't host any moon.
Sir, and they are capable of shifting their star from its position somewhat.
I didn't get your question.
Sir, like Jupiter, sir, Jupiter attracts sun toward itself. So, sir, sun
Yeah,
sun
absolutely,
changes.
absolutely. That basically that basic Newton mechanics in play, right? So like there would be something, then it would have a shifted kind of center of gravity, and then they would revolve around each other. Yeah, sure. If they have that close proximity to some kind of object, then they would. But that's why they occur in binary systems also, right? So they do these things with each other itself.
Okay, sir. Thank you.
Samir's hand is still raised.
Samir, do you have more questions?
No. I forgot to.
Yes, Devang.
Okay. Devang?
I sorry. I asked this question even in the chat box that is there a possibility that we can misclassify low mass stars as brown dwarf?
Yes, we can, I guess.
And then how
We
can
can
we
do it.
overcome it? Like,
I don't know.
okay.
You maybe look at the spectra. There is a particular stellar spectra. There is particular. It showcases the nuclear synthesis happening in it, the spectrum, and then we can maybe look at how we can get past that barrier of identifying, um, like
Maybe a presence of
indication of.
certain element like can differentiate the
Yeah, the
low.
presence of certain molecule in the cloud, molecule in their atmosphere that differentiates generally. This is the strategy for every given object in astrophysics to classify it from different things. So like in every given intersection, we look at the spectra only. We try to map that spectra to some like reference spectra in those object frames, and then we try to understand what's going on and how did we misclassify that.
Okay. Thank you.
Okay, so there is one
So there
question
was
in
a
the
chat
chat
going
box.
on between Soham
Huh. So that is by
and
Anish.
Devang, I
He
guess.
is he is
Okay.
asking what some of the sorry,
No. Go ahead.
were some of the brown dwarfs discovered through gravitational microlensing in case they were orbiting in front of or in the vicinity of a star, cause both emit X-rays.
I don't know. I will have to check. There might be research publications which lead to
Right.
this question.
Okay. And then there is one question by Ankit. He is asking, what kind of systems does normally a brown dwarf belongs to? I mean, is it a part of a solar system or
No,
like
it
star
is
system
not
or
part of
occurs as a
solar
solar,
system.
solar object?
They normally occur isolated systems. They are normally isolated. They don't particularly occur with associated with any system.
Then is Karthik. Do brown dwarfs on the upper limit can be excited or say pulled by a massive object or a merger to become a main sequence if fusion starts up?
Can you please go again? slowly.
Do brown dwarfs on the upper limit can be excited or say pulled by a massive object or a merger? So he's asking basically, can brown dwarf be converted to main sequence stars? No.
Oh, that's those stars even can't go into the main sequence stars. Why would no? I don't think so.
Then brown
But
dwarfs are
like, how
gaseous
is
or
that? How is
terrestrial?
that possible? I want. Who is this? Who did ask this question?
This was asked by Karthik.
Karthik, can you
Karthik, you can
specifically
unmute
say is there
yourself
in the
and
meeting?
explain.
Hi there.
Anji.
Am I audible?
Yep.
Actually, I was asking that sometimes whenever, say, main sequence R is going along a heavy object and it pulls or creates tension around it. So, if Brown draws on the very upper limit, uh, instills the same tension due to some other object or creates a merger with another Brown dwarf, could it be initiated to a main sequence?
But in general, mergers do not go into main sequence. Mergers make something kind of mergers are normally they don't entirely merge to form something of a higher mass thing, but they disorient their entire systems. That is what the understanding of a general merger is. So I don't think so. This would happen. Like
So,
I don't know what would happen in
usually,
this.
Brown dwarfs,
It's
if they have completely formed, they can't gobble up more interest to become main
yes,
sequence.
they can't gobble up.
Okay. Next question is by Ujjwal.
Thank you.
He is asking, as the brown dwarfs are moving independently around any galaxy, is there a possibility of two dwarfs colliding with each other and then forming a bigger brown dwarf? Similar kind of question.
I guess is that answered as well?
He is again asking, like, can two brown dwarfs collide to form a bigger brown dwarf?
Dwarfs can collide to form brown. Interesting question. What do you feel?
Well, the probability of
I don't know
colliding
what
two
to.
brown dwarfs is very less, in my opinion.
Yes, because they are isolated systems only. So they colliding would be pretty rare itself. If that has happened, then there would be maximum a couple of publications, if there would be.
Right. We do not have any like example of such event as of it, so we cannot say anything about
No.
it. Right. Next we have question from Devan. Is there a possibility that low mass stars can be misclassified as? Is this asked before?
I asked it.
ये वक्त पूछ लिया था ना ये वक्त पूछ
Oh.
लिया था
And then we have Soham. He is asking, is dwarfs more warmer than Jupiter? What dwarfs?
Dwarfs are warmer. Yeah, they are. They have high surface. They have high surface temperatures. Brown dwarfs, I think he means to say, but okay. Himadri had posted a couple of questions, but I think those are questions asked by someone else.
Just a second.
So yeah. Brown dwarfs are warmer than Jupiter. They have higher surface brightness. I guess that itself indicates that they are warmer inside also. Jupiter is very cold. It is 128 Kelvin surface brightness, surface temperature.
Okay. So if there are more questions, you can ask in the chat box and you can unmute yourself. We will wait for 2 minutes for the new questions. Otherwise, we will wrap up the meeting. Okay, so I guess there are no more questions. We can end the session. So with this, we end this session.
Sir,
We hope you all find this session very helpful. Yes.
sir,
Yeah, you can
what
go on.
kind of reaction, sir, what kind of reaction is going on inside brown dwarfs? Means, sir, like inside sun fusion is happening. So, sir, something like that.
So there is, I guess I mentioned there is electron degeneracy pressure which acts. It is not entirely the fusion which is responsible for the contracting galaxy gravitational force, but there is this electron degeneracy pressure which in the quantum mechanical state it develops the pressure and thus it contracts the gravitational force. Also, there was this. Is that answered? Was it? I'm not sure. Okay, so there is this question, interesting question about by Torel Sanyukta S. What made them decrease the temperature? It is in the chat box. What made them to decrease the temperature? So basically, they don't have enough mass to produce energy by nuclear fusion, as we know. But the small amount of energy, like these objects emit energy, obviously they will emit some energy according to the surface brightness temperatures. So they emit small amount of energy, and so they kind of reduce the heat stored in them. And the fusion is no not that much to produce the energy. So the energy storage in them, like basically the energy storage reduces by this energy emitted, and it cannot be by um, that much fulfilled by the electron degeneracy pressure heating up the inside of the brown dwarf. So basically, the the parent gas collapses when the clouds are formed, and they gradually cool and fade with cosmological time. Maybe cosmological time, as in they take very many years to do that. Like the age of brown dwarfs is not yet kind of discreetly known to us. Also, I felt that was a good question worth answering.
There are some new questions in the chat box. You can look into them.
Why Jupiter has so strong magnetic field even after being gas giant? I guess Devan has answered that question in a better way. The next is under what star category brown dwarfs fall, and are they capable of becoming a black hole? No, they are not capable of becoming a black hole. Everything is capable of becoming a black hole, like even Earth is, but it needs that much small space to compose itself in it. So, but yeah, you don't have that kind of energy to go into the black hole. So it is less than 1.5 stellar masses easily. So uh, that would just violate the Chandrasekhar limit if it becomes a black hole. It doesn't even become a white dwarf star. So that's the point. The evolution of brown dwarfs after they have cooled is not yet known because it takes very many years, and we don't have that much theory according like in that in this field. And under what star category does this form? It doesn't fall under any star category. That's why we had to uh, add three categories to the spectral classification of stars: L, T, and Y. And the Schwarzschild cell radius is different. Is that it, Gaurav? Yes.
Yes, I guess we do not have any more questions. So yeah, we can end the session. We hope you all find this session very helpful and informative. And thank you, Vaya, for the time, talent, and expertise you have given for this session. Also, we got a massive attendance of 125. So yeah, that's good. And sorry for the technical difficulties some of you face in joining the session. And we will be having the IBAC orientation section next week, where we will answer all your questions related to the Isaac Bhopal Astronomy Club. Thank you everyone for joining the session. Bye.